Question B4, 3 parts. When describing a sound, what do you understand by the terms frequency, quality and amplitude? Part 2. In the measurement of sound, what do you understand by the terms LAdB and LAEQ TdB? And thirdly, describe the strategies you would adopt to reduce the impact of road noise on a planned building development. So for the first part, frequency is the rate at which air molecules vibrate and actually transmits the sound at that rate of vibration. The quality defines the frequency that makes up a particular sound. Sound produced with just one frequency is often called a pure tone. And amplitude is a measure of the actual loudness of the sound, the intensity or the energy, if you like, of the actual sound itself. In the second part, LAdB, the A-weighting measure of the actual sound itself, or the sound pressure level, takes into account the depressed sensitivity of the human hearing at lower frequencies. And it actually correlates well with annoyance of sound and the loudness of sound. As you can see here in this graph, where we've got these low frequencies right up to about 1,000 cycles a second, we've actually got a depression in how sensitive the human ear hears those sounds. So what happens is that the actual amount of energy that's actually, or sound that's actually produced at these lower frequencies is discounted, and a slight increase is given to the frequencies at between 1K and 8K. In terms of the LEQ dB, this is the equivalent sound pressure level, and this is the average sound pressure level which would result in the same energy at the measurement point for a specific time. Perhaps the best example to think about here is that if we've got a sound, say we're measuring the sound of a train passing by, and there's one train an hour, then we could actually measure the sound at the intensity when the train passes, and that would give us one level. But over the duration of that 1 hour, if there's only one train, it's actually going to be relatively quiet. So by measuring it over the time period, say t, over the hour, we get, if you like, an equivalent sound to that, just that one spike that occurred for a minute or so as the train passed by, and we get a much lower reading. And again, we can actually sort of take that to the LAQ, and we can actually sort of do that in terms of how we would actually hear the sound as well. So the low frequencies are measured. So the LEQ method is to actually average it out over a period of time where we've got discrete incidence of sound. If we've got continuous sound, then it's less appropriate. In terms of tackling the source of the sound, perhaps in terms of actually sort of reducing the sound, the first thing to do is to actually tackle the source of the sound. And road noise can be reduced by various means: banning the traffic, moving the traffic, restricting the traffic speed, the type of traffic. Do we actually get rid of the lorries and the buses, etc.? Do we change the road surface? And here in this graphic, I've got sort of the effects of porous asphalt, a smoother road surface that generates less tyre noise as the vehicles actually pass over it. And as you can see here, that before the application of the surface, 70% of people were annoyed, and then after the application of it, only 27% were annoyed. But it's not a particularly cheap treatment. Once you've actually exhausted the actual opportunities for actually sort of noise reduction at source, the next step is to think about where you might locate your building on the site. And here the strategy is that if you can actually put your building at a greater distance from the source of the sound, the better. So that each time we double the distance from the sound itself, we get about a 6 decibel reduction in the actual intensity of the sound, because the actual sound itself has been spread out over a much greater area. But each time we double the distance, we get that 6 decibels. So the initial moving away from the sound source is actually very productive. Further displacements become less and less productive. Allied with the sort of the placement strategy is inserting a barrier as close as possible to the sound source. This does two things really. The first thing is it increases the distance the sound has to travel. It's actually got to climb over the obstacle and get down the other side. So it's as if we're actually moving the building further away without doing it. And also some of the sound is actually reflected back into the space itself. Reasonable sort of lower frequencies, perhaps less at higher frequencies, would be this sort of the actual take on this. As sound moves through the air, it can be reflected off hard surfaces, so that if we've got particularly the ground itself or other buildings, but if we've got hard surfaces between the sound source and our building, we can actually get sort of sound reflected off that ground, so there's actually sort of very little absorption of the sound. But if we've got sort of surfaces that are much softer, and that might be through vegetation, water, whatever, not water, through trees and vegetation, then they will absorb some of that sound and actually reduce the actual sound level as it comes to the actual sort of. Once we've exhausted the strategies outside the building, the next phase is to actually look at how we can actually change the building design itself, and that should be the last thing we actually think about. And in terms of the actual building design, the windows, any penetration through the building fabric is always going to be the weakest link. So to keep the distribution and size of the windows to a minimum on the facades that are facing the noise is the strategy. Where we have got windows facing the sound, the actual source of sound, then double glazing with perhaps laminated glass, so we've got two sheets of glass that have different sort of elements to them. If it's not possible to actually change the window sizing, then perhaps thinking about the internal layout of the design, moving the spaces that are less noise sensitive, circulation spaces, kitchens perhaps, towards the sound source, and those spaces that are less sensitive away from the sound source. And in terms of the other areas, if we actually make the actual surfaces as thick and as heavy as possible, then we can actually sort of reduce the sound impact.